If you're like me, you're curious about the universe, the stuff of space and time, and the forces that bind us all together. Today's guest wants to encourage that curiosity and believes physics can be accessible to everyone. He's author and physicist Sean Caroll, this week on Story in the Public Square. Hello and welcome to Story in the Public Square, where storytelling meets public affairs. I'm Jim Ludis from the Pell Center at Salve Regina University.
And I'm G. Wayne Miller, also with Salve's Pell Center.
And our guest this week is Sean Caroll, the Homewood Professor of Natural Philosophy at Johns Hopkins University and fractal faculty at the Santa Fe Institute. His most recent book is The Biggest Ideas in the Universe, Quanta and Fields. He's joining us today from Baltimore. Sean, thank you so much for being with us.
Thanks very much for having me.
You know, your 2022 book, The Biggest Ideas in the Universe, opens with the admitted fantasy of people checking out of work at the end of the day, headed down to the local watering hole, and kicking back, enjoying an adult beverage perhaps, and talking about physics. It's a very democratic approach to an idea or a topic that is often considered elite. Where does your commitment to popular engagement with these issues come from?
You know, I've often thought that for most people, science is pretty interesting, right? If you take away the idea that there are courses you will take in high school and you will get a grade and you have to memorize a lot of things, people want to know how their universe works, how the atmosphere works, how chemicals work, how biology works. And we have to sort of restore that wonder and awe in the universe. And it happens at different levels. Maybe some people just want to hear the occasional headline. Some people want to dig more deeply. I think that we have a rich enough ecosystem of ways to talk about science these days that we can keep everybody happy.
All right, so I'm going to totally take the host's prerogative on this. And I shared with you that I had recently just posted on Facebook this just a question about the universe that had kept me up at night. That the universe is expanding infinitely. Am I expanding infinitely too?
You are not.
Why not?
Well, that's the harder question. You didn't tell me you were going to answer that. That's a good one. I mean, the short answer is that you are being held together by the forces inside your body. If you want an analogy, there's a famous analogy for the expanding universe, which is just a rubber sheet that you're sort of pulling on all ends. If you sort of set some pennies or other coins on the rubber sheet and you pull the rubber sheet, the pennies will move apart, but they won't grow bigger. Because even if they were being pulled by the expansion of the rubber under them, they're being held together by their internal forces. It's more or less the same story for you. The universe is not trying to pull you apart. It's just that out there in between the galaxies, more and more space is being created. So we see distant galaxies move away from us and we say, look, the universe is expanding.
Thank you.
So when were you first drawn to physics?
I was one of these lucky kids. You know, I stumbled upon my life's work pretty early. I was maybe 10 years old, so that's around fourth grade. And it wasn't even science fiction or movies or anything like that that got me. It was literally reading books about physics, about cosmology and particle physics and gravity, the Big Bang and black holes and quarks and leptons. Nobody in my family had any interest in this stuff. None of my teachers were especially expert, but somehow I found it. I really don't know how. And then I would hang out in the local public library and read all the books I could get my hands on.
So then you became a physicist. When did you decide that in addition to that, writing and broadcasting for the popular quote-unquote audience, people like us, was also a critical part of a scientist's work, your science certainly?
Yeah, actually, I don't necessarily think it's a part of every scientist's work. I think that the field as a whole, physics or other fields, chemistry or history or whatever, have obligations to reach out to the broader public and explain what it is they're doing, especially with a field like mine, where we're talking about what happened near the Big Bang, okay? that is not going to help cure cancer, make a better smartphone, anything like that. There's no immediate, tangible technological or economic benefits. Nevertheless, as a species, we devote resources to answering these questions. There's no point in devoting any resources to answering these questions if the scientists find out the answers and then don't tell anybody, right? So I think that we do, as a whole, have an obligation to do this. And I personally was just always interested in writing and speaking and thinking about these things in a sort of connected, discursive way. So for me, it's something that I can do that hopefully adds value to the world.
Sean, the flip side of the sort of the role of the physicists in this is the receptivity of the public for, and frankly the readiness of the public for, conversations on these types of topics. When we talk about basic science literacy, how does the American public do?
There's a joke among physicists and astronomers that if you're on a plane ride and the person sitting next to you says, "What do you do for a living?" If you want to talk to them, you say, "I do astronomy." And if you don't want to talk to them, you say, "I do physics." The word physics rubs people the wrong. Astronomy sounds fun, like there's the sky, and physics sounds a little more hardcore about those things. Look, I think it's pretty clear that we don't have enough scientific literacy in the United States or in the world. And to me, the important aspect of scientific literacy is not a list of facts that people have memorized. It's an idea of science as a process. How, if you were a scientist, would you go about answering a question like, why does the sun shine, or something like that? Why is the sky blue? There's an answer to why is the sky blue, but it's much more important to think about, what would I do to find out? The idea of proposing multiple different hypotheses and then comparing them against data, against experiment and observation, and then saying, all right, this hypothesis I was really very fond of, but I have to reject it now because it doesn't fit the data. That's where science is really at its best.
So how does the philosopher's mindset, and you are a philosopher in addition to a scientist, how does that inform or help your work as a scientist, as a physicist?
Yeah, I discovered philosophy much later, and it wasn't even when I was an undergraduate at university. And it wasn't even much later than that I realized that my research work in physics had an overlap with modern philosophy. And in retrospect, it's not that surprising. Physics asks these huge questions about the very nature of reality itself, right? I mean, how unsurprising can it be that occasionally those are going to bump against philosophy questions? Why is there something rather than nothing? Why are there 3 dimensions of space rather than some other number? What does it mean to say that a certain physical theory is natural or unnatural, okay? Likewise, in biology or neuroscience or artificial intelligence, we have areas of science that clearly involve philosophical questions. So what I came to understand is that the way of thinking that is characteristic of philosophy, a very patient, very careful, very rigorous argumentation, really sifting through all the assumptions that one makes and making sure you're not taking things for granted, that can absolutely be crucially helpful in shedding light on some questions we would absolutely think of as science questions.
So I'm a historian, and there was a time through most of human history, most of recorded human history, where the space between philosophy and science was negligible, right? What have we, it might be re-asking the question you just answered, but what have we lost by separating the world of ideas per se from the world of science?
I think that there is a reason why I chose the title that I have here at Johns Hopkins. It wasn't a pre-existing title. I got to ask for it, Homewood Professor of Natural Philosophy, because that's what science used to be called. If you were talking to Isaac Newton or Galileo, they would have called themselves philosophers, natural philosophers. In that case, it was to distinguish natural philosophy, understanding the workings of the natural world, versus theology and other kinds of philosophical questions. Nowadays, that still is there, but also we would distinguish things like moral and political philosophy, questions of value and ethics, from questions of how does the fundamental nature of reality work. So I want to bring those back together, which is why we coined the term, or we re-energized the term natural philosophy. And in fact, here at Johns Hopkins, we're trying to build up a forum in natural philosophy. We're having guest speakers and a big conference in May, and it's very, very exciting because I do think that the difference, the distinction between them is artificial. I think that there are questions about how the natural world works. Some of them are best tackled using the traditional methods of science. Some are best tackled using traditional methods of philosophy. Some of them are right smack in between. And it's only because we have universities and we need to have departments with department chairs and hiring committees that we even treat these as separate things at all.
So you mentioned Newton and you mentioned what you're doing now at Hopkins. When did specialization become the norm? You're not doing that. Newton didn't do that. Some of the people, some of the philosophers of antiquity, Plato, for example, did not do that. They brought them together. When did specialization?
There's a joke among philosophers that says, as soon as a subfield of philosophy starts to make progress, it separates off and becomes its own field. So everything that we think of as science used to be part of philosophy, but eventually it branched off. And you know what? I'm not against that. I think that it's a simple fact that the total amount of human knowledge has grown enormously. If you're in a PhD program in chemistry or biology or physics, you have a lot to learn. Your plate is full. You don't really need to learn a lot about ethics or metaphysics or epistemology. I mean, maybe it would be nice if you had some basic understanding of the history of science, philosophical questions in science, but mostly you're trying to learn about chemistry if you're trying to become a chemist. So what's important to me is that we talk to each other. It's not that every individual has to be an expert in everything. I think that time's long since passed when that's a feasible request. There's just too many things that there are to know. But we should be able to communicate, and I think that's where we're really falling down. You get two people in very different departments at a university together to talk about some question they're both interested in. And there's an enormous language barrier. They have different ways of thinking about things, different favorite results that they refer to, different standards for what's interesting or successful. And I think that that would be much less of an issue if we just more frequently interacted with each other.
Now, so Sean, your series, The Biggest Ideas in the Universe, is conceived of as a three-part series of books. The first two are out. The first was really about the world of Newtonian physics. The second, which was just published in May, is about the world of quantum mechanics and quantum field theory. For the uninitiated, what distinguishes those two approaches to physics?
That's a great question. You know, I think that what we call the classical paradigm for physics that started with Isaac Newton is kind of how we intuitively think about physics. You know, if you're thinking about throwing a baseball and you have where the baseball is, you have how fast you're throwing it, in what direction, in principle, you could calculate where it goes. That's the example that you would always have in mind in classical physics. You have a system, you have some properties that the system has, you use them to predict what will happen next. And quantum mechanics comes along in the early 20th century, and it completely overthrows that paradigm because there's this whole new set of rules in quantum mechanics about what happens when you measure a system. It turns out that an electron, a tiny subatomic particle, when you're not looking at it, when it's just sitting there inside an atom, is spread out in what we call the wave function of the electron. If you're a chemistry major, if you're taking your chemistry courses, you learn about orbitals of electrons. These are different shapes that the electron cloud can have. But when you look at it, you never see these clouds. You see a point, you see a dot, you see as if it's a particle. So quantum mechanics, for the first time, introduces this idea that what you see when you look at a system is different than the way we describe it when you're not measuring it. And honestly, physicists are still struggling to wrap their brains around that.
Yeah, I think, because the question that my historian's mind wants to ask is why? Like, so why is the process of why is the experience of observation, which feels passive, affecting what the experiment is producing as a result?
That's right. And this is a perfectly good question because people try to bring up analogies or metaphors, right? Or they try to tell stories about it. They say, well, quantum mechanics is like trying to take a photograph of someone who doesn't want their picture taken. So the act of taking the picture changes the look on their face, right? These analogies are bad. A point across, but they make you think that maybe if you were sneaky and took the picture very carefully, you could get them exactly as they normally look. Whereas quantum mechanics is saying something much more dramatic. And ultimately, you know, honestly, I can't really give you a complete answer to that question in less than a half an hour lecture, which is probably not what you want right now. Right. The very short answer is, yeah, that's the way nature is set up. Sorry, you know, that's the rules that were laid down. And the feature that really matters is that you and the rest of the world, the electron or whatever, are entangled with each other in some way. That's the word we use in quantum mechanics, where the state that you find yourself in is correlated in a very central way to the state that the physical system finds itself in that you want to measure.
Okay, so I'm going to expose myself as being really just a neophyte in all of this. But you mentioned entanglement, and this is the other spooky part of quantum mechanics that I really have a hard time processing. But as I understand quantum entanglement, two subatomic particles will behave the same way, even if they're separated by vast distances. Is that approximately right?
It's approximately right. What I would say is when you have entanglement between two particles, which you may or may not have, you can have two particles, maybe they're entangled, maybe they're not. But if they are entangled, then like you said, the precise way to say it quantum mechanically is if you measure something about one particle, you instantly know what the measurement outcome will be for the other particle. You didn't know it before, but once you've measured the particle near you, now you know the state of the other particle far away.
And what does that tell us about the universe?
You know, the only honest answer is we don't know, in the sense that we don't agree. Different physicists have ideas. I have ideas. If you read the most recent book, Quanta and Fields, the spirit behind these recent books is I'm not trying to delve into the controversial parts of physics. I'm not trying to be speculative. I'm not talking about the multiverse or string theory or whatever. I'm trying to stick to the things that we all agree are more or less on solid ground and will still be taught 500 years from now, right? But the foundations of quantum mechanics is not there. That is not something we agree on and will have a consensus about. So I mention it. There's different approaches. There's what's called the many worlds interpretation of quantum mechanics. There's hidden variable theories of quantum mechanics. There are epistemic theories of quantum mechanics, which say it's all in your mind. It's all about what you're thinking and what you know, not what is out there in the world. So we debate this, and we don't really have anything settled quite yet. I think it's kind of embarrassing that we don't, but that's the state of play.
So you talk about thinking, and it's all in your mind, and also you mentioned the word speculation. Can you speculate for a moment on this issue? What role will AI play in coming breakthroughs in physics? Or what role is it playing even now?
Yeah, AI is very important in physics and in science more generally for the very simple reason that over the past several decades, we developed the capacity to collect enormous amounts of data. I remember when I was a graduate student at the Harvard Smithsonian Center for Astrophysics, they were very proud that they had made a map. They called it a map of the universe, but it's really a map of a few thousand galaxies nearby our galaxy. Pretty impressive, and we learned a lot from that. These days, we regularly make maps with millions and millions of galaxies, and they're just growing with time. So you want to ask a question. What have we learned? What are the properties of this gigantic data set? The Large Hadron Collider at Geneva, which is the particle accelerator where they discovered the Higgs boson, has so much data in a single event, a single collision between two particles, that we literally can't record all the data. We throw away all but 1/1 millionth of the data because there's just too much of it. So the sifting through all of those possibilities and asking what we learn is something that is tailor-made for AI. It's not that AI is not very good at my job, at being the theoretical physicist proposing new models, right? AI is not a good model for Albert Einstein or for Isaac Newton, but for helping us understand what the phenomena are that we're trying to account for and what patterns are there, what regularities, AI is wonderful.
So we've been talking space and time, and here's kind of a semi-funny question. How do you find the time for all of the rest that you do, starting with your podcast? Tell us about that podcast, and if you have a second, how do you find time for it?
I do have a podcast. I love doing the podcast, and I'll tell you the story, which is that I wrote a book a while ago now, almost 10 years ago now, called The Big Picture. And in this book, I'm trying to sort of tie together in an interdisciplinary way all the different aspects of the natural world, from physics to life to consciousness, and see how they all fit into one picture. Even if we don't know the picture perfectly, we have very good reason to say that it all fits together. And so to me, this was a tremendous thrill because I got to talk to biologists and philosophers and neuroscientists, et cetera. And then when the book was done, I had no more right to call them up and say, can I come talk to you? The podcast, which is called Mindscape, and it comes out every Monday, is just me talking to leaders in the intellectual world about one thing or another. It's not just physics. There's a lot of physics and philosophy, but a lot of other things. In the last couple of years, I was very gratified. I spoke to someone who's an economist, Daron Acemoglu, who went on a short time later to win the Nobel Prize in economics. And then I previously spoke to two writer-directors from Hollywood called Daniels, who wrote and directed Everything Everywhere All at Once, who, after appearing on my podcast, went on to win the Oscar for Best Picture. So I'm thinking that I'm getting the right people in my conversations.
Yeah, so you mentioned consciousness. And so as we've been having this conversation, I guess the question that leaped to my mind is, do these insights about the universe tell us anything about human consciousness?
I think they tell us a very tiny amount. I'm not going to claim that understanding physics better teaches you what consciousness is or how it works. But I do think we have very good reason to think that whatever consciousness is and however it works, it's compatible with the laws of physics as we know them. There are people out there who think that we won't ever understand consciousness until we change the laws of physics. I just don't think that's right. So I have an argument for that, and we can go back and forth, but also there's work to be done within physics and, if you want to call it, complex systems science, explaining how you can go from a bunch of electrons and protons and neutrons bouncing against each other to 85 billion neurons connected to each other in our brains that gives rise to consciousness. That's a long road to go. We have plenty of steps to be filled in.
So, Sean, you were raised Episcopalian, but you are now an atheist. Talk about what led you to become an atheist.
Yeah, I think it's pretty simple. I don't necessarily think that people are the own best diagnosers of how they made these changes intellectually, but as I learn more and more about how the natural world works, there seemed to be less and less reason to think that there's anything supernatural about it. And I think that, it's kind of a liberating moment when you finally say, like, actually, yeah, I get why 2,000 years ago this would have been an attractive idea. We don't need it anymore. Maybe we can pick and choose the best parts of the religious traditions that we're left with and get rid of the parts that aren't doing good anymore.
Yeah, Sean, you teach at one of America's great universities. You've got both this public and this academic profile in this space. I'm wondering if you've given thought to the preparation that students you're receiving have before they get to the university level. Are we producing the right students with the right STEM skills coming out of high schools for the kind of research that we're talking about here?
Well, one thing I would say is I'm just as interested in and caring about non-STEM skills as STEM skills. STEM skills are very, very important, but so is writing and the arts and the humanities more generally. People need to know how to read and write as well as to add and do science. So I think it's all important. And I think that overall, I think it's not exactly news to say that the American primary and secondary education systems aren't the best in the world for lots of reasons. We don't put resources into it. We have a very bizarre public school system where if you just happen to live in a neighborhood where property values are low, your school system has no money. And this is exactly kind of backwards to me. It's, the people who live in the rich areas who need less investment in their public schools, but they get the most. I think we could easily imagine overhauls to the curriculum that focus on, as I said before, methods and practices. How does science work? How do you think like a scientist rather than memorizing list of species or planets or whatever?
So we have just about a minute left, Sean. And what is your scenario for the end of the universe? And I realize you'll probably need more than 30 seconds, but if you can.
It's no time soon. The universe is expanding.
It just seems like it sometimes.
And it's expanding, as we discovered in 1998, it's expanding faster and faster. We see no reason to think that will ever stop. We live in an accelerating universe. So meanwhile, all the stuff in the universe is burning fuel, right? Our sun is burning fuel. Other stars in the sky are burning fuel. So if you give me a quadrillion years from now, the last star will have burned up all its fuel. There'll be no more stars shining. There will be black holes, but those black holes gradually evaporate and everything is moving apart from everything else. So after a huge number of years from now, we'll be left with nothing but cold, desolate, empty space in what we call the heat death of the universe. That's the future you have to look forward to.
Well, that is a cheery note to leave it on. Sean Caroll, the book series is The Biggest Ideas in the Universe, and the podcast is Mindscape. Thank you so much for being with us. That's all the time we have this week, but if you want to know more about storing the public square, you can find us on social media or visit pellcenter.org, where you can always catch up on previous episodes. He's Wayne, I'm Jim, asking you to join us again next time for more Story in the Public Square.